Thank you all for making it out. This is our last talk for today. It's been a pretty great one. I hope you've had some good interactions, some good talks today. This talk is Dr. Rebecca Bilbro. She's a data scientist, programmer, speaker, teacher, all sorts of things. Very, very great. And we have Patrick Deziel, software engineer specializing in machine learning. They're here to talk to us about data types. Take it away.
Thanks so much. Can you hear me okay? All right. Welcome to our talk on conflict-free replicated data types. We're going to call them CRDTs probably for most of the talk because it's a little bit of a mouthful. So you'll just have to remember that CRDT means conflict-free replicated data types. So we're going to be talking about how we think that CRDTs might help improve code collaboration for the Python community. We're going to start by defining some terminology from the distributed systems community that help contextualize why CRDTs are so cool and useful, and then we'll give a high-level introduction to CRDTs, followed by a more in-depth description of our own open source Python implementation of conflict-free replicated data types and a little demo, fingers crossed, and followed by some takeaways for you. So first off, who are we? We are Rebecca and Patrick. We both work for a company called Rotational Labs, where we build small to medium-sized geo-distributed systems. What is a geo-distributed system? Maybe you are asking. Well, according to the granddaddy of systems, Leslie Lamport, a distributed system is one in which the failure of a computer that you didn't even know existed can render your computer unusable. And this is something that we think about a lot at Rotational Labs and something that our tools are designed to help with. But potentially you are thinking, well, I don't have anything to do with distributed systems. And if I do one thing in this talk today, if we can give you one idea that you walk away with, it's that you actually interact with and have a lot to do with distributed systems. And so we're going to start by giving you a sense of how you might be encountering replication and conflict, which are two of the biggest problems in distributed systems in your everyday work. So hopefully this sort of interface resonates for many of us, right? So we're working collaboratively with a teammate doing Python together, and we're using some kind of cloud-hosted Jupyter Notebook solution. So let's imagine that Patrick and I are collaborating on some code together, some yellow brick code. Patrick lives in Minnesota. I live in North Carolina. So we are working from opposite sides of the country in the same Jupyter Notebook, right? And so the way that we ensure in this implementation, this is not our implementation, this is Databricks, but the way that we ensure that there's no conflict between the changes that Patrick's going to make and the changes that I make is that when Patrick is in this cell outlined in orange, it's locked to me. I can't make any edits while he's working in this cell. And that's a really good way to make sure that we don't end up with conflict. But it's not so good for collaboration. So we're curious, can we do better than this? So potentially you've also encountered this when you are reviewing code from somebody else that's written in a Jupyter Notebook and giving feedback to them. You know, adding a small comment to a Jupyter Notebook totally changes the underlying JSON data, right? So even if you've made a change that doesn't actually change any of the code, let's say just a comment, you know, you add a line so it changes the numbering for all of the subsequent lines. You also change the ID of the cell, and you probably change a bunch of metadata too, depending on whether your operating system is the same, whether the installation of Python has changed, whether the version of Jupyter is different. So a lot of kind of metadata has changed, which makes it a little bit complicated to figure out how to coordinate changes that are being made by collaborators in Jupyter Notebooks. So why is that so tough? Well, before we talk about the distributed systems context and why that's tough, let's talk about just a single non-distributed system, a single server. This is going to be super convenient, right? Because it's, just imagine a single database. We can all write to it. We can all read from it. And it's going to be really, really predictable about how it responds. It's going to be whoever says that they want to write this value first, the next read is going to read that value. So that's really nice. That's convenient until something bad happens. And when something bad happens and that data store goes down, the system becomes completely unusable to everybody. Nobody can write, nobody can read, and if there was any data in transit, it's probably gone forever. That's not good, and that's why we want distributed systems. That's why distributed systems are so important and valuable, right? They solve these two bad problems where if one of the servers goes down in a distributed system, doesn't matter. It will just route all of the requests to the remaining servers, and the system remains available. And also, if we have data replication happening, we have multiple copies of the data, then we don't have to worry about losing volatile data. This is why distributed systems are great, except it does add some complexity. And the complexity comes in the form of inconsistency and concurrency. So servers in a distributed system, they need to communicate to stay synchronized. And communication takes time. And the more servers you have that have to communicate together, the more time it's going to take. And that time has a cost, because if there's enough of a delay in communication, we can have the situation where two different clients could try to write to the same object different values in a way that the system can't put into order. So it doesn't know how to put those operations in order anymore. And what we call this is concurrency. So they're called concurrent writes. And so from the system's perspective, they've actually happened at the same time. Well, did they actually happen at the same time, like clock time, watch time? No, probably not. But you know what? In distributed systems, we can't rely on physical clocks anymore because we have space and time separating us, time zones. A lot of distance. So instead, we have to use algorithms called logical clocks. Logical clocks get us part of the way there by putting things partly in order. And then we have to use heuristics to establish a total ordering of events. So these are some of the things that we need to understand as a precursor to appreciating kind of why CRDTs are so neat. So what is a conflict-free replicated data type? Well, it's a data structure that is designed for replication. It's a very good, easy, lightweight alternative to the other tools that we have for synchronization and coordination in a big distributed system. One of the examples that we saw earlier was locking, right? So locking is super effective, but it does limit collaboration. Another alternative is consensus algorithms like Paxos and Raft. These are very effective, but very heavyweight ways of maintaining synchronization across the system because they require every server that's participating in the quorum to agree on every single write before anything gets written. So that's intense, and it's difficult to implement. You need experts to do it for you. But CRDTs, by comparison, are actually relatively lightweight and simple. So what you need for a CRDT to implement it is really just some representation of mutable state, and you need some function that can merge two states together in a deterministic way, so that if you merge everything and I merge everything, we're going to get the same answer, even if we're far apart from each other. So that function, the operations need to be idempotent, associative, commutative. Tell me if you've heard this song before. What does this sound like in Python? Sounds like a set, right? That's a very good intuition. And another really good intuition is that you can actually implement simple CRDTs and compose them together to get more complex CRDTs. So here's an example of that. So two of the most simple types of CRDTs are called G counters and G sets. So a G counter is a monotonically increasing counter across all of the replicas in the system. And each of the replicas has a unique ID. So the counter value at any point in time is equal to the sum of all of the values across all of the replicas. And you can kind of imagine how you probably would implement this as a dictionary in Python. So a G set is just a set that only supports appends and adds, right? We can't delete anything, so that's basically a Python set. So we can do really neat things to add features. So let's say we want to have a grow-only set that does support deletion. Well, what we can do is build a two-phase set, which is basically just a combination of two G sets, so that one of the sets can keep track of what we call tombstones, which are operations that record deletions, right? And we need to keep a memory of deletions, because when I run all of my operations and you run all of your operations, we need to make sure that we both delete anything that's been deleted. Another type of compound CRDT, and in fact the one that we're going to talk about from our open source implementation, is the sequence CRDT. And this is what you need in order to kind of reconfigure, reimagine a Jupyter Notebook that is more collaborative. So I'm going to turn it over to Patrick now to talk about how to make that happen in Python.
Hey, everybody. So we are at a Python conference, so I thought it would be interesting to show how we built our little implementation CRDTs in Python. And our kind of idea here was we wanted to create a collaborative notebook that's kind of like Jupyter, but it's built using CRDTs from the ground up. So what that does is that allows us to basically facilitate a greater level of collaboration between like me and Rebecca, for example. And if you think about some of the requirements would be for this, we would need to have some high-level operations. So we're inserting and removing specific notebook cells. So if you imagine your Databricks notebook, and if you can imagine like within a single cell, you're editing the text in the cell, so you're inserting and removing characters. So if we support merging at both of those levels, we can enable consistency for the entire notebook. So one of the key understandings of this is that those two cases are kind of similar. They're both ordered sets. They're both lists of things. And so the cell data is just a sequence, and the list of cells in the notebook is also a sequence. So in our implementation, we have kind of what's called more like an operational CRDT. So instead of replicating the individual objects within the CRDT, we're replicating the operations that get applied across all the peers in the network. So to achieve this eventual consistency that Rebecca was talking about, we need to, all the peers need to agree on the set of operations and also the ordering of all their operations within the entire set across all the peers. So one way we can do this is that we can do some trickery with the operation IDs. So we can give each operation a unique ID such that it's easy for us to figure out which one comes before the other ones, ordering. And we can use the client name and also the logical timestamp, can combine those together to get our operation ID. And so then on top of that, we apply some simple heuristic like sorting rules such that lower timestamp values always go first, and we order by the client name to break ties. So it's a bit arbitrary, but at least we get some consistent state out of it. So then once we have this total ordering of operations, if we want to present it to the user, what we have to do is that we have to just run through the list of ordered operations, and we have to apply them to the object list that we're currently maintaining. And this is like the logic, at a high level, it's pretty simple, but there's some trickery involved here where we have to be careful about where we're inserting things. So this Bob at 5 operation and Alice at 2, they're actually referencing the same source operation. So they're both trying to insert after that A value. So we have to make sure that we're ordering them in the correct manner such that we're not violating these ordering rules that we just defined in the last slide. We also have to take care of deleted objects, and this is not like your Python list where you're just like removing the object and forgetting about it. You have to make sure that that object still exists in the list, because future operations might reference that object, such as this Alice at 5 one. So what we do there is we use a tombstone flag similar to the two-phase set. So if we kind of zoom out and we look at the use case between two different peers, what Alice has to do if she wants to sync her state with Bob is she has to send her set of operations over to Bob. And Bob has the responsibility of doing a local merge from his end of his state of the notebook and Alice's state of the notebook. Since the CRDTs are, they fulfill all those properties that Rebecca was talking about, what this means is that each peer at the end of this, they can realize the same set of objects at the end, because it doesn't matter which order we apply all these operations in, because there's a consistent ordering and each peer knows about all the operations in the set, we can render the same object state. So at this point, we're going to try a little demo of our little open source implementation called Irene. And so here, what's happening is that we have a little interface here, and we can create a peer called Alice. And you'll see immediately that we added a operation here to the oplog. So this is an insert of a cell object. So this is the cell that already exists, and this behaves kind of like a text editor. The only thing is we can't actually run code here, which would be cool, but we don't have that implemented in this demo. So Alice can enter some text here in this cell, and what happens is that it gets decomposed into these individual operations. And now the CRDT has a few more operations in the set. We can also delete stuff and re-add it, and it'll just be creating more operations, and we can create new cells here or delete them as we please. And then it gets a bit more interesting. We add a second peer called Bob, and Bob can type in some characters as well. And you can kind of think about for a few seconds what happens when you actually merge these two. So what happens is that it actually creates two notebooks in the shared state. And the reason this happens is because Alice and Bob both did an insert cell operation, and the CRDT doesn't know that those are kind of like supposed to be the same cell at that point because they haven't merged together. They started as independent notebooks. So now we can actually say Alice is doing some data science. And imports something, and then syncs with Bob. So now Bob has the new state as determined by Alice. And then Bob, on the other end, say enters a comment like, maybe we should use time series split, and then sends that back to Alice. So what this is like is a kind of unidirectional syncing, which is not entirely impressive. Like, you don't really need a CRDT to do that. But what's more interesting is that if we do some concurrent operations here, so Alice loads a data set, and then Bob loads another data set. What happens here is that when we sync, these are concurrent operations. So this is a demonstration that it's handling both of the inserts without stomping over each other, which is kind of what we want the CRDT to do. We want it to resolve these conflicts in a way that makes sense, like sense from user perspective. And then we can make it more interesting. We can add another client called Charlie. So he just joined the team. And he gets the updated state from Bob. And then Charlie wants to do some cleanup here. So he does some refactoring, I guess, then syncs with Alice. Alice now has synced state with Charlie. Now Bob still has the old state because he hasn't synced yet with anybody, with Charlie or Alice, but he can sync with Alice, and now he has Alice's state as well. So what we've achieved here is a eventual consistency with CRDTs. Pretty cool. So now we can go back and look at, pull back the curtain a little bit and show you how this actually works in Python. So at the base of this solution is our sequence CRDT, which we've been talking about, and it's kind of the base class that we're using because it stores like a very generic set of objects. And so we have our notebook and our cell, which are both subclasses of the sequence. And then the sequence itself contains like a unique ID, which represents the kind of the client, which is using that particular notebook, and then a G set, grow only set of the operation set, and then a clock because we have to keep track of the current logical time so we can create operations with the correct IDs. So that's the main design. If we go down and look at what does a CRDT actually look like in Python, this is our implementation of a grow only counter. So it's our logical clock. And you'll notice that it's pretty straightforward. You might have thought it was a little bit more complicated, but it's actually just managing a dictionary in Python, which is pretty useful. The only restriction is that we have to make sure that we are using unique IDs every time we create a new G counter and merge them, because if we don't, then the G counter cannot distinguish different peers. So that's the main constraint. Is actually a very more difficult problem, but we did not address that in this demo. So more complicated code is our merge function and our sequence CRDT. And for this is our composite CRDT, right? So we have to merge two of the underlying CRDTs. We have to merge the operation set, and we have to also merge the clock, so the G counter and the G set. We also have to do some like a recursive merge of the subsequences. So what that means is that our notebooks will contain a sequence of cells, and cells themselves are CRDTs. So we have to merge at two levels. So this is why we have to do a recursive merge in this merge function right here. Then this is our object tree. It's just kind of a representation of the current state of some of the items that are in the sequence, but this is an order representation that the user would see. So this is kind of like a bookkeeping mechanism to keep track of the current state that's in what we were looking at earlier. So this is probably the part of the code where we've encountered the most bugs because the logic for actually finding where to insert operations within an existing set is actually kind of tricky, and it's hard to get right the first time. So there's cases where you have to find the target operation, or you have to handle the case where you have conflicting operations, so two operations that reference the same target, and you have to make sure those get ordered the same way across all the peers. So that's just a bit complicated to deal with. And now I'll pass it back to Rebecca to finish this out.
Thank you. So hopefully everybody is pretty excited about CRDTs and distributed systems now. But I did want to just kind of admit that there are some limitations, right? It's not perfect for every situation. So first and foremost, this is a form of eventual consistency. And what that means is in the absence of new writes, eventually everybody will find the same state. That does not work for all use cases, right? So in some cases, we need something faster. So eventual consistency, I think, works well for some applications, but not for all. So that's one thing to keep in mind. Another big thing to keep in mind is that this is an append-only data type, right? So that's fine when it's the first few 100 operations or 100,000 operations. But imagine that we keep editing these Jupyter notebooks forever. Eventually we're going to end up with a very, 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 very long log that we have to send back and forth every time we want to do a synchronization. Now that's not really a good idea, right? So we're going to end up with buffer issues. We might end up with egress cost issues. And so at some point we're going to have to deal with pruning or compaction so that we're not sending massive logs back and forth every time we synchronize. But, you know, those limitations aside, we think that it's pretty neat and actually kind of surprising. CRDTs have been around for more than a decade. And it's kind of surprising that they haven't found more usage in kind of everyday programming. So we're hoping that this talk will be the beginning of a change there. We see lots of possibilities for, you know, collaborative editing, for merging, forking, branching, commenting, all kinds of kind of more collaborative ways of working together. So we hope that you will check out our little open source implementation of CRDT in Python. It's called Irene. You can find it in GitHub in the rotational organization. You're welcome to fork it, look for bugs, just tinker with it yourself however you like. We also want to point out that there's actually a lot of great tools out there that came around before we started working on Irene that are custom designed specifically for working with Jupyter notebooks like diffing and merging and that kind of stuff. So NBDime is a really great one. There's actually a number of them. We also want to give a shout out to the Paratext project. So Paratext is another open source implementation of CRDT for rich text collaboration done by Martin Kleppmann and his research team. Speaking of Martin Kleppmann, if you're interested in learning a little bit more about CRDT, he has a really nice write-up on his blog and some videos about CRDTs, the hard parts. And another great resource is Michael Whitaker's Consistency in Distributed Systems lectures. There's a section all on conflict-free replicated data types, which we strongly recommend. And we hope that we have whet your appetite and got you a little bit curious about CRDT and distributed systems. And there's no questions during the talk, but we will hang out. We hope that you'll come and chat with us and ask us your questions, and we can learn more about how you might be interested in using CRDTs in your work. Thanks very much for coming.
Thanks to Rebecca, Patrick, and we made it, guys. There's some lightning talks downstairs and more talks tomorrow. Thanks all again.